Okay, we're recording now. So, well, let me introduce you. Today, we have here Kayla Wright. She's from University of Oregon now, recently, and she's going to talk about a geometric model for semilinear locally gentle algebras. So, thank you again, Kayla, for accepting to give this talk in this hour. It's too long for you, I think.
Thank you, Carlos, for the introduction and the invitation to speak. I'm going to be speaking about some joint work with Esther Banaian, Raphael Bennett-Tennenhaus, and Karin Jacobsen about these semilinear locally gentle algebras. If you go ahead and look at the chat, I have a Google Drive link to the notes for the talk. I find it helpful to have them right in front of me. And sometimes when I'm nervous, I tend to go a little fast. So sometimes it's nice to see kind of what I was talking about on the last slide. So if you can all open that if you're interested in following along today, that would be great. But yeah, thanks for the invitation. So the plan for the talk today is we're going to first review what the notion of a path algebra from a quiver is and modules over these path algebras. And then we'll be discussing a generalization of the path algebra, which we'll call semilinear path algebras. So the way that I kind of got involved in this project is I really liked topological models for algebras. So the theme of the talk, all the donuts that I came up with, we have kind of these like regular donuts. You can think these are kind of classical geometric models for certain algebras. And we're going to be looking at a geometric model for these kind of twisted generalizations. So that's what these twisty donuts are meant to help you kind of follow along during the talk. So the third part of the talk will be kind of introducing some topology and showing how you can visualize these algebras and modules for the algebras. And please feel free to stop me if you have any questions throughout the talk. I'll try to monitor the chat if people wanted to chat questions, but you can also feel free to unmute and just ask me verbally. Okay, so I'm sure that this will be review for a lot of you, but we're going to be generalizing a lot of these notions, so I'll go ahead and just review path algebras and modules for them. So we're going to start with a quiver, which you can think is an ordered pair, Q0, comma Q1 of vertices and arrows, and we're just going to allow any directed graph. So for instance, I can take this path graph on 3 vertices. My set of vertices, I'll try to use numbers, and for the arrows, I'll try to use these Greek letters. Each arrow alpha from I to j has a source that I'll denote S of alpha. So this is just where the arrow is starting from. So this vertex I, and it has a target. So this is where the arrow ends. And we call them quivers because we're going to be doing algebraic things with them, not graph theoretic things. Okay, so from a quiver, you can obtain a path algebra. So we're first going to start by fixing an arbitrary field K. And the path algebra that I'll denote KQ is the algebra generated by the paths that you can get in the quiver, thinking about walks in the graph. And the multiplication in this algebra is just concatenation of these paths when it makes sense. So if we take our example from the previous slide, we have the quiver on 3 vertices here. Then the path algebra associated to the quiver is going to be generated by these lazy paths that I'm going to denote epsilon I. And you can think, for example, epsilon 1 is just the path in the graph Q, where I'm just staying at the vertex 1. So for each vertex in the quiver, you're going to have one of these basis elements for your algebra. And then we just see kind of what paths we can take following the orientation of the quiver. So all of the arrows are going to be generators for the algebra. And in this particular case, I can walk from 1 to 2 to 3. So the concatenation of the arrow alpha beta is also an element of my basis. So the path algebra is generated by these 6 things. And it turns out that this is actually isomorphic as an algebra to the matrix algebra of lower triangular matrices. And you can kind of think that the isomorphism goes as follows for kind of all of the diagonal elements. If you think about the matrix where you just have a 1 at this entry and zeros everywhere else, this is kind of in bijection, with this particular basis element epsilon 1. So the diagonal entries are going to correspond to the lazy paths. And then the elements below the diagonals are going to talk about paths from 1 to 2, paths from 2 to 3, thinking about the index of the row and column of the matrix. So that's how this isomorphism works. And as matrices, you can think about how these are going to be multiplied together, or you can think about looking at the quiver, how things are going to get multiplied together. So in general, we have that all of the lazy paths are idempotent elements of the algebra. So if you take epsilon 2 and you square it, it's the same as just staying at the vertex epsilon 2. So we have this relation. If we have that the source of alpha is 1, for example, then we have that alpha times epsilon, if we have that the target of alpha is 2, for example, we can think about doing the multiplication alpha times epsilon 2, and that's just the same as doing the arrow alpha. So when it makes sense to multiply the lazy paths, you can do it, but in the opposite order, for example, if we were to try to do first alpha and then epsilon 1, this doesn't make sense with the orientation of the arrow, so we set those multiplications equal to 0 if you can't actually see it as a path in the quiver. Okay, so this is the path algebra and the way that the multiplication works. And just pay attention that we did have this isomorphism to this matrix algebra, because this will come up later. Okay, so sometimes we want to impose some relations on our algebra. So we might want to kind of quotient out by an ideal so that maybe we get some nice conditions on this path algebra. So for instance, if we take the quiver we've been looking at, maybe I can look at the ideal generated by this 2-path alpha beta and set that equal to 0. So we can look at something called the bound path algebra. So if we take this ideal I generated by the 2-path alpha beta, then we're going to have nearly the same algebra. We have now 5 basis elements, but we've set this alpha beta equal to 0. And this is also going to be isomorphic to a matrix algebra where we can think this lower entry is now having to be 0. So people consider lots of different ideals. I'm sure that everyone probably knows more about this than me here. But the way that I like to kind of think about these conditions on the ideals are maybe.
Sorry, could you go back to this last isomorphism? This is only vector space, isn't it?
Yeah.
Right. Yeah. Okay.
Thank you. Yes, as vector spaces.
Yeah.
Thanks. Are there any other questions?
Yeah. Or you cannot put. I mean, you can do it as an algebra, but yeah, I don't. Yeah, you need to put some special things in the entries below the diagonal, otherwise it will not usually be 0, right?
Yeah. Thank you for making me be careful.
Yeah, the right-hand side is not an algebra.
It's not an algebra, yeah, of course, yeah. Unless you, the relation.
Unless you put in the relation.
Yeah, in some way.
Yeah. Thank you.
Sorry.
No, you're okay. All right. So what I want you to focus on, though, is that we can impose some relations on the paths that are in the quiver. So for example, if we have like some sort of cyclic behavior in the quiver, then if you think about doing paths in the cycle, or you keep going around in this cycle, you can have infinitely many paths. And maybe we want to look at some sort of finite dimensional version of these algebras. So if we have some like infinite dimensional algebra, maybe we're trying to choose an ideal that forces it to be a finite dimensional object. We also might want to look at different ideals that allow for nice like homological properties. So we want the modules to look nice, we want nice like AR theory, and we want to have some kind of control over what's happening. So those are maybe some classes of ideals people care about. And then also we can try to model algebras from other fields using certain ideals. So this is kind of motivating why people mod out by these things. What we're going to be looking at are generalizations of gentle algebras. So I'm going to go over what that is. So I think that in general, these are like some of the nicest bound path algebras, and you can define it by exactly how the ideal behaves. So I have 4 conditions. I'll start with 2 of them here. We say an ideal is gentle if you have at most 2 arrows stopping and starting at the vertex I. So that's already a pretty strict condition. We also need that the ideal is generated by paths of length 2. And then there's 2 other conditions that we need for this gentleness. And you can kind of think about them in these 2 pictures that I have down here. The idea is you can't exit out of a vertex or enter into a vertex in too many ways without getting killed in the ideal. So for instance, if I go along this arrow alpha prime, I should only be able to go out one way without having been killed if I took a different entrance. So this dashed line is supposed to represent the relation alpha beta in the ideal I. So we have that this path is going to be killed in the ideal, but this path is something that's non-zero. And the same is true when you're exiting. So here, if I have this arrow beta, I can only go out of it one way without getting killed in the ideal. So that's what these 2 conditions are saying here. So again, we're going to be looking at these generalizations of gentle algebras. So we have a lot of control over what the ideals look like and the ways that you can enter and exit paths without being killed in the quotient. So the goal is we want to try to understand indecomposable modules for algebras that come from quivers. So I'm going to go ahead and review what it means for you to be a module for a path algebra. So you can think that a module for the path algebra KQ is just a quiver representation, which means that you're just assigning K vector spaces to the vertices of the quiver and K linear maps to the arrows. So if we take this quiver again, you can assign whatever vector space you want to each of the vertices 1 through 3, and then you can represent these linear maps as matrices. So I just have some matrices that I have here. This is going to be a module for the path algebra or a quiver representation. If we are looking at KQ mod I, then it's kind of the same exact thing. We still want to assign vector spaces to vertices and linear maps to arrows, but we want the relations to be respected by the maps that we associate to the vector spaces. So let's take this different quiver Q, this 3 cycle, and let's take the ideal generated by gamma alpha, which is denoted by this kind of angle that I have here in gray, and then the relation beta gamma. The idea is if I look at a module for KQ mod I want to make sure that when I do the linear maps associated to gamma alpha, I get 0, for example. So if I look at the assignment of the linear maps I have here, I have that this map on gamma is just the 0 map. So that will impose the relations that I want. If I do this concatenation, I'm 0. And if I do beta gamma, I'm 0. So this is going to be a module for the bound path algebra. So there are some central questions that people are interested in studying. Can we classify all the indecomposable modules for a given bound path algebra? And the one that we'll be most interested in kind of looking at today is, can we visualize the modules using some sort of geometric or topological means? So here's kind of a preview of the result that we're going to try to get at for these semilinear locally gentle algebras. So for certain KQ mod I, you can classify all the indecomposable modules visually, and there have been kind of a school of people who have thought about these sorts of things, and it's very beautiful work in my opinion. The preview is we have some kind of algebraic objects over here. So take, for example, a bound quiver algebra, and you want to see it, and you want to also see what the modules look like for that algebra. The idea is that we want to come up with some sort of dictionary between topology and algebra to see these sorts of things. So in this preview that I have here, we can somehow look at this bound quiver algebra by looking at a triangulation of some sort of surface. So I have a torus with two boundary components on this side, and then I've just drawn like a cartoon of triangulating it somehow. I have these black points on the torus, and I'm kind of connecting them up in some sort of special way. And there's a way that you can visualize these algebras with a topological surface. And after you've triangulated this surface, you can superimpose arcs on top of it. So this arc that I have drawn in pink gamma, you can just put on top of your triangulated surface. And this is supposed to show you what a module for the bound path algebra looks like. So this is what I mean by geometric model. So what we're going to be trying to do is trying to come up with a geometric model for like different types of algebras, kind of generalizing work that lots of people have done on this topic. So, but first I wanted to talk about what exact algebras we're going to be studying. We're going to be giving this geometric model for what are called semilinear locally gentle algebras, and they're indecomposable modules. So the main idea is we have these kind of two adjectives to define. The semilinearity is just generalizing what you can put on the vertices for these algebras. So they're going to generalize like the field aspect of it, as well as the linear maps that you can put on the arrows. And this locally gentle condition is just giving a different condition on the ideal of relations that's going to allow for some infinite dimensionality. Okay, so I'm going to try to carefully go over an example of one of these algebras. Okay, so here's the recipe to get a semilinear path algebra. So our original ingredients for the path algebra were a field and a quiver. The semilinear ingredients, we're going to take a division ring. So we're going to allow for some non-commutativity of the elements that are going to be put on the vertices of the quiver. We're still going to have an underlying quiver. And then we're also going to endow it with a little bit more information. We're going to also associate an automorphism of the division ring to each of the arrows in the quiver. So you can kind of think about that as the initial data, and then we're going to look at like modules over these things. And this generalizes the original story, because if we choose K to be commutative, and we just associate the identity automorphism to each arrow, we'll recover the usual path algebra. Okay. So I tried to pick like a kind of hard example. It's still a very simple quiver. We're going to have this quiver with 3 vertices, but we're going to take the division ring, that's the quaternions. So we want to think that they're generated by these I, J, and K elements. And if you don't remember the relations, I put them all here. So this is how kind of I, J, and K relate to one another. And the example we're going to look at is just going to be like one non-trivial automorphism for Q. So remember, we need an automorphism to each arrow in the quiver. So I'm going to just let sigma alpha be the identity automorphism. So that one's not doing anything interesting. But I'm going to look at some non-trivial automorphism on beta. Namely, if you look at kind of this formula that I've written here, you're concatenating by this element that's kind of a nice special element in the quaternions that mimics kind of rotation by an angle theta. So we'll choose some angle theta between 0 and 2 pi, and this is going to kind of visually look like a rotation by that angle as an automorphism. So what we want to know is, what does this semilinear path algebra look like? And this is going to be the notation I'll have. So the division ring will be here. The kind of set of automorphisms I put on the quiver, I'm going to denote sigma underline, and then here's our quiver Q. Okay. So let's kind of compare and contrast what happens with the path algebra versus this semilinear path algebra. So we still have the property that the lazy paths are idempotent elements of the algebra. So when we square them, they're themselves. That hasn't changed. We still have that if we take two lazy paths that are on different vertices, those are going to be 0 when we multiply them in the algebra. We still have that the lazy paths are pretty well behaved in general. So if we have a arrow from I to J, we have the like usual multiplications on the lazy path is still going to be the same. We also are going to allow the lazy paths to commute with any element of the division ring. So I can kind of pass scalars through any of my lazy paths. The main difference is when we go through arrows. So in the usual path algebra, we have that any scalar is going to commute with a path in the path algebra. So we can kind of pull them around wherever we want in the multiplication. But if we have some non-trivial automorphism, we have to kind of be careful when we're pulling them through where we want to keep track of what's happening with the automorphism. So let's say I wanted to pull this scalar, I guess, to the other side. I was trying to multiply them in the other direction. I need to make sure that I twist it by the appropriate automorphism, namely sigma alpha with this notation. Okay, so everything basically looks the same except for this last condition that I have here. So let's go through this example and talk about different multiplications and how they'll work. So recall we put the identity on the arrow alpha in this kind of more interesting automorphism on the arrow beta. We have that the semilinear path algebra still has the same basis as the usual path algebra, but some of the multiplications look a little different. So I have some examples here. If we wanted to multiply a scalar times epsilon1, a scalar times beta, we can kind of still use the same rules that we had in the usual path algebra. So for instance, epsilon1 times beta is still going to go to 0, so this will be 0 in the semilinear path algebra. But if this concatenation makes sense, so for instance, in the second line here, epsilon2 beta does make sense, then we still have that it's the usual beta in the semilinear path algebra. If we wanted to multiply something like scalar times alpha, scalar times beta, we have to make sure that we're looking at what the automorphisms are. So in this particular example, if we wanted to pass this scalar mu kind of through alpha, then we have to make sure we're twisting by the appropriate automorphism. So since we're passing through alpha, but this is just the identity, this multiplication will be lambda mu alpha beta. But if we were to pass through this kind of more complicated automorphism, if we're looking at this multiplication here, passing mu through beta, we need to make sure that we're twisting by the automorphism on beta, which is this q inverse mu q. So this is just some examples of multiplications in this algebra. Again, it has the same basis, but the multiplication has to respect the automorphisms we've chosen on the arrows.
Sorry, Kayla, by any chance, can you recall sort of like a non-simply laced thinking algebras from the right choice of fields, or I mean a division ring and automorphisms?
Non-simply laced, like if there are
Yeah,
multiple arrows between.
No, it's like B2 or Bn, right? I mean, which has
Yeah, so is there like a semilinear analog for these things if I have multiple arrows, let's say here?
No, what I mean is, okay, we can speak about this after the talk.
No, but I'm going to leave and I want to hear this.
Okay.
So I think what Hipólito is asking is, can you realize the classical quiver algebra of, say, type V2 as one of these guys, but using a simply laced
So
underlying quiver, just by putting on some.
Yeah, okay, I understand the question now, I think. Not to my knowledge.
all right.
Yeah, I wouldn't know how to do it.
Yeah,
I don't know. I don't think so, but
yeah, because Bn is like An, except that sort of locally at one, you can look at two arrows. It feels like two arrows going out, right?
Yeah.
And to two, it arrives only one. I mean, it's like you need to put some weights in the and I mean, I can talk to you before when Pablo leaves, and then I.
Like it's like the valued quiver
Yeah,
representation.
exactly. Yeah.
Yeah, I don't think that this is the same. I don't have a great like reason why.
Okay.
I've just
All
never
right.
seen it mentioned in the literature, but I can
All
also ask Raphael because he knows this stuff very
Right.
well.
I see.
Yeah.
And sorry, maybe in the same line, is there any reason why you want to just take a skew field and not say something that might have more automorphisms? Like maybe some.
Yeah, you can take
ring?
as complicated of a division ring as you'd want,
No, but I mean, why do you want a division ring? Just to have.
Bases.
just so that there's kind of some interesting non-commutativity properties through the arrows, I think is the idea.
Okay, but I could take like a non-commutative ring instead of a non-commutative field.
Mhm.
You want
And-
vector spaces, right? I mean, it's
Oh, well, maybe a semi-simple non-commutative.
well, I should speak about I have a project of
sure,
that.
we should talk about it.
Yeah.
Okay, sorry.
That's okay. Do you feel your question was answered?
Yeah.
Okay.
Everybody
Great.
was-
Okay.
Yeah, please.
I'm gonna go ahead and move on from this example, but I'm happy to talk more after the talk.
Right.
Okay. Cool. So I want to try to give an analogy for what this isomorphism looked like on kind of the previous section. So we saw that as an algebra, this is isomorphic to this matrix algebra of lower triangular matrices when we were looking in the classical path algebra case. So is there some sort of analogy for what this algebra looks like? And it turns out that you can kind of realize it almost as a matrix algebra. So it'll look like you can put things in some sort of lower triangular matrix, but there are some more complicated elements that you can realize on these stars rather than just elements of a field. So in this particular example, you can think that this algebra looks like a matrix algebra where you're allowed to put any element of the quaternions on the diagonal. And this is because the lazy paths are kind of behaving in the exact same way as they were in the usual sense. But you have something more interesting happening on the lower diagonal entries. You have that these these are going to look like bimodules where you're respecting the semilinearity of the arrows that they're kind of corresponding to. So for instance, I have kind of what the multiplication will look like for things in this thing that I'm calling M. So if you focus on the diagonal entries, again, these are just going to be regular multiplication in the quaternions. But if we look at these entries kind of below the diagonal, they're going to be kind of bimodule actions. So I don't know if people are interested in these formulas, but the idea is we want to respect what was happening on the arrows when we are looking at this isomorphism of algebras. Okay, so the goal of the project is to try to construct a geometric model for semilinear path algebras. And it's going to look very similar to the preview that I had on a few slides ago. The idea is where we want to look at something that we're going to call a bound locally gentle quiver. And this is going to be visualized by a pair of almost triangulations. We're going to call them dissections. That just means that there are some collection of non-crossing arcs on a surface, but maybe they're not maximal in some way. The automorphisms of the arrows that are giving our semilinearity are going to be realized by what we call a labeled tiling of the surface. And it turns out that you can look at all of the indecomposable modules for these algebras as strings and bands. And these are going to look like certain arcs and closed curves on the surface. Okay, so I'm going to start talking a little bit more about the topological setup. Okay, so we're going to let S be an orientable surface with or without boundary. So this picture here, I just have a sphere with two boundary components removed. That's what these kind of things are. And then we're going to have a set of marked points that I'll call M. And we want to think about these marked points as being partitioned into two kind of alternating sets. So I'm going to have vertices in black and vertices in red. You can think that these are like V and V dual. And we want to have for every boundary component, if I have one black marked point, I need to have like a red complementary one. If I have these black punctures, I need to make sure that I have their dual, etc. Okay, so you can think an arc on a surface is a curve whose endpoints are in M, but they're disjoint from the boundary of M. So we don't want the curve kind of touching the boundary in any way. We only want it touching it at its endpoints in the set M. A dissection is going to be a collection of non-crossing arcs, and this is up to kind of being able to wiggle the arcs around with like an isotopy. And a face is going to be some connected component of the surface minus the dissection. So I have an example here.
Sorry, the dissection doesn't need to be maximal, right? I mean, you can have a non-maximal.
Yeah. So if I were to say triangulation,
Right.
that is maximal.
Okay.
But I'm not going to insist on that.
Okay.
Yeah. So we have an example here. And if you look, this face here doesn't look like a triangle. It's actually too big. So this is a dissection of the punctured polygon. So I have this set of marked points in black that I have here, A, B, C, D, E, F. And then all of my arcs are connecting those black points. And for this example, I wanted to kind of keep it simple without any of the duals, but the dissection arcs are labeled by these numbers. Okay. So
yeah, technical question about this dissection. So the duals would be like one for each face of your dissection?
Yes.
I see.
And we'll see this same example in the dual dissection of it in a second. So
All
you'll
right.
see. You're exactly right. Yes. Okay. So from a dissection, we want to get our quiver with relations because we're trying to model this like quiver algebra. So this is pretty classical. The idea is that the arcs of the dissection are going to be in bijection with the vertices of the quiver. The arrows of the quiver are going to be kind of looking at different arcs that come from the same marked point with respect to some orientation. And then the faces of our dissection are going to give us kind of our ideal of relations that we're looking at. So let's look at the same example that we had from before. We have our dissection of the punctured polygon or pentagon. If you look at all of the arcs, we have 6 different arcs. These are in bijection with each of the vertices of the quiver. And then when it comes to connecting it, we just have to kind of see what things are adjacent to each other. So one kind of easy thing to see maybe is if you look at a face, so this big face that we have in the middle here, if we fix the, what orientation did I pick? If we fix the counterclockwise orientation for this surface, then I have 5 points to 2, 2 points to 3, 3 points to 4, and 4 points to 5. This is kind of the way that I get the quiver quickly. I just look at each face, and then I take the orientation that I've chosen for the surface, and I draw these arrows. So that corresponds to this 4 cycle that you've seen here. Another thing that you can do is kind of analyze at each marked point what arcs are adjacent if you look at this local picture. But that gives you the arrows in the quiver. And then for us to get the ideal, we want to look at the internal faces of the dissection. So what that means is we only want to look at the faces that don't use any boundary components. So the one that I was focusing on just a second ago is the only internal face, because if I were to look at, for example, a face like this uses the boundary of the surface. So we're not going to call that an internal face. So the only relations that we get have to come from the faces that only use the arcs of the dissection. And what we do is we just take all of the two paths there. So for example, since we're looking at this big face here, I want the concatenation of 2 and 3 to be 0 in the quotient. So that's giving the relation that when I do delta beta, that needs to go to 0 in the quotient, etc. So you can kind of think about the angles of the internal face giving you the relations I.
Sorry again. Yeah. Suppose that I would like to ask from a different dissection. Suppose that the edge 1 that goes from A to C is removed and you put an edge from A to D.
A to E or A to D?
D. Right?
B.
D, yeah.
D.
D.
Sorry.
Yeah, going to the top
Okay.
somehow.
Like, I could replace this with this.
Okay, but could you replace that with the one that goes from A to? I mean, I think you might be able, yeah, from here to here.
No, you can't do, I think I saw what you were doing. You asked about this.
Yes.
This is the same as the boundary component right here. Because you could just like isotope it like this.
Even if you have like a dual point between A and D?
Yeah, yeah.
I see.
So we want to think about the quiver in the way that we're getting the quiver without the dual dissection.
Yeah,
The dual dissection is going to be giving the way that we put the automorphisms on the quiver.
I see. Okay.
Okay. Any other questions about this setup?
Yeah.
Yeah.
Go ahead.
So if we were to put
So,
a
okay.
black mark here, then we could do that. Like if we did this,
Right, yes.
then
But
it would be something non-trivial.
yeah, and in that case, suppose that we have this case, right? That we can actually do that. You would have a face which is not internal. Yeah. Would you have a relation coming from this face? No.
Yeah.
Suppose that the edge 1 is not there anymore for some reason.
Mhm.
Right? So then you would have an arrow from 3 to 2 and an arrow from, or vice versa, right? An arrow from 2 to this new edge. Yeah. So
like if we're looking at things around a puncture,
yeah.
is that what you're asking? Like, do you get relations from the puncture?
Not from the puncture, but from the concatenation. You would have like now 2 arrows which are associated to a non-internal face.
Mm-hmm.
Right? These 2 arrows would be in this composition would be in the ideal of relations or not?
No, I don't think so.
No? Okay.
Yeah.
Okay. Cheers.
Okay.
Sorry.
No, you're good. Okay. Great. So this is going to be our setup to get the quiver and the relations on the quiver from the topological surface.
Mm-hmm.
And now what we really want to do is try to recover this semilinearity on the surface somehow. So the first idea we had is we are trying to somehow see on the surface the arrows for certain. But the kind of idea, the roadblock that we had was when we do have these internal faces, it's hard for us to distinguish, like with this one internal face, how we're going to label all of these automorphisms because we don't have a nice way to split it up at the moment when it's this big giant face. So the idea that we had is we want to somehow be able to split up our surface so that we can look at how we can recover the arrows of our quiver in some nice way. And what we are going to end up doing is kind of coloring the surface into this different partition so that we can label the faces of this partition with automorphisms on the arrows. So this is kind of a preview of why we're going to do the following construction. Okay, so this is kind of motivating the dual dissection. So we've just been looking at the arcs that are in black. The dual that the dissection we were talking about has kind of this complementary thing that Hipólito hinted at to us. The faces of the dissection are going to be vertices in the dual, and vice versa. The vertices in the black dissection are going to be faces in the dual. Locally, we're going to see kind of things that look like this. So we'll take the example that we had previously, this punctured pentagon. We had the black triangulate, or the black dissection we were looking at. And then for each of the marked points on the boundary, I want these complementary points. And for each puncture I see, I want a complementary puncture in the dual dissection. And then what I want to see is that for a particular arc like 1, I want this kind of crossing condition here for its dual arc. So this is the dual dissection for the running example that we've been looking at, and we're going to be using it to model the semilinearity. Okay, so the idea is we want to use the arcs in red to cut up our surface. And what we realized is this is some sort of geometric realization of an algebraic result by Zembyk. So we call this Zembyk's algorithm since it was inspired by this algebraic results. But the idea when we're chopping up the surface is to try to look at vertices that have a relation going through them. And then we want to cut the surface at that particular arc if the vertex that it corresponded to had a relation. So we'll go ahead and just do this example. So we see that the relations that we had in our quiver all kind of depended on that big face. So the relational vertices, I'll call them, I've highlighted all in purple. They all have these kind of 2 paths going to 0. So the idea is we want to cut up the surface at these particular vertices. So I think the first one I chose to do, it doesn't matter the order that you do this in, is 4. So what I want to do is look at this intersection between the arc 4 and black and its dual arc and cut the surface there to kind of get rid of this relation. So if I go ahead and do that, there's some technicalities with like adding different marked points on the boundary, but you can kind of see that if we were to chop at this vertex here and chop this arc 4, now it's kind of cut in half. It looks like this, and this was the arc for now kind of 4 bar or 4 star copied twice. So when we get rid of this relation, we now have a surface that looks like this. And we can kind of continue going with all of the other relational vertices to see what we get. So here's the same picture that I had chopping at the vertex 4. If we now chop at the vertex 5, so this particular intersection that we see here, we're going to get the disjoint union of 2 different surfaces. So visually, we have this arc 5 is now chopped in half here. And you can think like part of this arc was this 5 star. And then we continue doing this for the 2 other relational vertices that we had from the quiver. So if we chop the left component at 2, then we're going to have, again, this arc 2 is now cut in half. Our dual arc is now this boundary component here. And we want to continue doing this until we have no relations or we see something that's of type A, D, or A tilde. So this, if you look at this particular piece, now just looks like something of type A. This looks like a pentagon, a triangulated pentagon. So we're done with that piece. We want to now look at the last remaining relation that we have at 3. If we were to
sorry, when would you have something of type D?
Type D?
Yeah, you say A?
That's a punctured pentagon.
Of course, yes. Sorry.
Yeah. So this one, oops. This one's now of type D, so it's good.
Yeah.
Yeah. So if we were to chop at 3, we get kind of this local picture if we chop at 3. And again, we're doing this for all of the vertices that gave a relation in the bound quiver. So the pre-Zembyk surface looks like this thing on the left. And once we've done all of these chops, we look like this disjoint union of surfaces. And if we were to look at the quivers that you get from these particular pieces, we have these 4 different quivers that are actually all of type A in this particular case. I guess this is type D too, but the idea was there was some algebraic result telling you how you can chop up an algebra that we realized you can do in this geometric sense. So the algebraic result that this was inspired by is saying that if you have some algebra KQ mod I, there exists this K algebra injection into this nice algebra that I'm calling A, that's a direct product of type A and A tilde algebras. So the idea is if you have some kind of complicated KQ mod I, there's a way that you can embed it into a nice product of algebras that are of type A and A tilde. And I think that we saw this for type D too. So yeah, so this is why we call it like Zembyk's algorithm, because we saw that this was an algebraic result that we were kind of doing topologically by accident. Okay. So our geometric realization of this result allows us to define what we called a labeled tiling of our dissected surface. So if we use this chopped up surface that I have on the left here, the idea is we are allowed to now look at this face in 4 different ways, with kind of looking at where we chopped along the dissection here. So the coloring of this partitioned face now are going to allow us to label the automorphisms in some meaningful way topologically. So we have our surface here. If we cut it up using Zembyk's algorithm, we now have a way to associate all of the automorphisms in some well-defined way. So yeah, our main result is that we have this geometric model now for these semilinear gentle, or locally gentle semilinear path algebras. So again, the way that the construction works is we have some quiver that's bound by relations, and the way that we can realize that on a surface is looking at a pair of dual dissections. The automorphisms that are associated to the arrows of our quiver are going to be given by this labeled tiling, the way that you color the surface after chopping it up using Zembyk's algorithm. And we wanted to look at what the module category looked like with the topology that we had. And this part was actually just using lots of other people's hard work. So it turns out that the modules for these semilinear path algebras are all just string and band modules. And this was proven by Raphael and his advisor. And what we can show then because of this is that there's this very nice like topological formulation of string and band modules that are in terms of these things called permissible arcs or closed curves on the surface. So I have an example of something that is known as a permissible arc here. I'll just do like one quick example of how you would get a module using this construction. Okay, so this is a construction by Bauer, Kohea, Samoas, along with Palou, Ploud, and Plamondon. They give geometric models for the module categories for KQ mod I. So if you have a locally gentle path algebra, there are bijections between topological kind of objects and these algebraic objects. So the permissible arcs on a surface, you can think that these are not, the endpoints aren't connected in any way, like the arc gamma that we saw, are in bijection with string modules. And closed curves, you can think this is just maybe like something that's isotopic to a circle on the marked surface, give you band modules in this module category. So this is theorems by other people. And because we have that these indecomposable semilinear path algebra modules are classified by strings and bands, we can kind of just bootstrap these 2 results together in order to see modules on our surface. So the idea is if we take this running example and we look at some permissible arc, so we have this thing gamma that I've drawn in brown here, there's a way that you can create a string module from this. And the idea is you look at the arcs that gamma is crossing in the surface, and that gives you kind of the string that you're going to be looking at or where the vector spaces are going to be on the quiver. So we see that gamma passes through 4, 3, and 1. So these are all going to be some one-dimensional vector space, we'll say here. And then the way that gamma is crossing the arcs is going to tell you kind of what the maps will look like here. Since these are kind of nice one-dimensional things, you can think that these are kind of the identity map, but we had all of these automorphisms that are on our arrows here. So the module structure that we endow these things with will come with this action of the semilinear path algebra. So similar to the way that we were talking about that example with multiplying things in the semilinear path algebra, the modules kind of work the same way. You have to be careful about different scalars if you're passing through some non-trivial automorphism. But essentially combining these two results, we're able to get that these arcs and these closed curves will give the string and the band modules for the semilinear path algebras. Okay, and I think that that's all I have. So thank you, and let me know if there are any questions.
Thank you, Kayla. It was amazing. I don't know, questions?
I do have a bunch of questions actually. So
You already did them all during your talk.
now, so you have this. So you have this dual dissection, right? And in some geometric models, this dual dissection actually is associated to projective resolutions of objects. I mean, I'm thinking more on the like Oberschkoll-Plamondon junction. Yeah, they have, you know, for the right category of a gentle algebra, you have like the black dissection is associated to the simple objects, and the red it's associated to the projectives, and in some sense this like, crossing up a red arc could correspond to a projective in a certain degree or something like this. Do you have something similar here? Do you have some kind of the projective resolution or projective presentation at least from your topological data?
Not that we've written down, but we were looking at like those exact works when we were trying to figure out exactly what we were doing when we were chopping up this surface.
Right.
So that would be a good thing for us to write down.
Okay.
Yeah, we definitely relied very heavily on both of those works that involve this dissection, this dual dissection. That's where we got them from. So I think it'd be good to look into that.
Yeah. Another question is, so you are chopping up this and you have like an embedding of, I mean, you have a monomorphism of algebras from using Zembyk's work. Now, this would imply that you have an embedding of module categories as well, or is
I think so, but I'm not super confident.
right?
Yeah, I
Or
think
is it
so.
of, yeah, I mean, you might have some functors going, right? I mean, because you have an induction going through this. Yeah. Okay. Yeah. Another question that I have is, which goes in another different line, is that maybe Esther is also involved in this supercluster algebra setting, right? That it comes from.
I don't know if she's done any of those things. I know of people who have, like
I mean,
my
maybe it's not
PhD
Esther,
advisor
but
likes those things.
yeah, but I mean, these supercluster algebras are those that have like you have a triangulation maybe, and then you have like a set to action, and you put signs in the different phases.
Yeah.
Do you think that you can categorize using a very particular example of all this work? You can categorize the supercluster algebras using your work by maybe putting like I don't know, the complex numbers and the signs depending on the identity and the conjugation or something like this, and choosing stuff like this.
Yeah, I think that these things could definitely be related. I know that we haven't thought about that too much, but
Okay.
yeah, I've been seeing a lot of people talking about these supercluster algebras, and I think a lot of them feel very similar to the things that we've been thinking
Yeah.
about. Maybe, yeah.
Yeah, because it looks like essentially you have a very very nice way to define the sign by just taking, like, I mean, not that not any division ring, but the complex numbers, right? And then you have this non-trivial isomorphism, which is the conjugation, and this might, instead of
Yeah.
having one different endomorphism for each of the arrows, you might choose the same for the whole of the face. This might give you some nice way of categorizing the supercluster algebras.
Yeah, maybe. I'm not really familiar with like the topological model for these. I've seen like people talking about it from quivers, but I'm like trying to think of the surfaces that it would look like.
Yeah, Ana Garcia Ilsner has some work on this, definitely.
Yeah.
She was presenting this last week actually, but I could not attend her talk because I was teaching. But yeah, there is some very nice work doing in that respect, and I think this yeah, this can give a very nice categorification of that.
Yeah, I'll definitely let my co-authors know that we have things to think about. That sounds cool.
Yeah, it's pretty nice. Yeah, it was an amazing talk. Cheers.
Thank you.
Well, I don't have any questions, but I do have a comment that is, those are really beautiful drawings that you have there. I was
part of them, so
very
Let's put some light. Sorry. Yes.
I don't know if there anyone else is.
I know. Yeah.
Okay.